Probably.
All right, good morning, everyone. Today we're Team 2, and today we'll be showing you how to create a simple Zigbee communication network using XBee components. My name is Scott Oliver.
I'm Jennifer Becker.
I'm Paul Solomon.
Andrew Warner. You heard? So just a little overview of what we'll be discussing. First, we'll just kind of go over what exactly Zigbee is, the difference between the different XBee product lines. Then we're going to kind of give you a little example, a project that we've kind of worked out. We'll show you how to set up the hardware side of it, the software side of it, and then how to actually collect incoming data using just a simple Python script. So what is Zigbee? Zigbee is basically just a technical standard for communication protocols. It uses small, low-power digital radios for personal area networks. It's used a lot for just smaller personal projects that don't transfer very large data packets and don't require a lot of power. XBee is Digi International's in-house kind of like branding for Zigbee communication, like the module brand. That's what we'll be going over. And here's just kind of there's a lot of different XBee products out there, their whole like family product lines. They're all kind of similar. They vary based on the antenna they use, the connectors they use, and just the different software capabilities they have. The primary difference between them is the topology. The network mesh topology that you use. So there's three main types of mesh network topology. There's a star, tree, and mesh. The star is mainly for short distances between the node and the coordinator because they communicate directly with each other. The tree can be used for larger distances because there's a router that can be used in between to relay information from the node to the coordinator. But there's a set path that the node has to go directly from the node to the router to the coordinator, whereas a true mesh is a lot more versatile because all of the components, the routers and nodes and the coordinator can all communicate with each other. So for our sample project, we'll just be giving it a simple example of taking a node connected to a moisture sensor that gives off its reading in volts. Then we'll have data transmit using the Zigbee receivers, transmit information from the node to a coordinator where data will be collected using a Python script.
All right, so we're actually going to walk you through the hardware part first. So we're going to need two XBee Digimesh 2.4 units, which I'll explain what that is in a little while. We'll need a protoboard, an XBee protoboard adapter, and that's necessary because the XBee themselves, they don't fit in the protoboards because of the spacing. You need an XBee USB Explorer. You need the interfacing tool, which is the XCTU, power supply, something to input voltage. We're going to be using a sensor, but you can also use a potentiometer, and then the Python script. So the 2.4 module that we're using, 2.4 stands for the frequency it's using, 2.4 gigahertz. It is a Digimesh firmware, which means that this particular model, which we're using in our actual project, it has a self-healing and ad hoc mesh network. Self-healing meaning if you have several nodes and one drops, the entire system doesn't go down, but it will reroute information. And then ad hoc meaning it will do it automatically without having a user dictate that. Also, it has a sleep synchronization. So there will be one node that will say it's time to sleep, and all the other nodes will follow orders, which is really necessary for a low power consumption like our 480 project. And then all nodes can sleep. A couple slides ago, Scott was talking about the different types. There was the tree one that had router nodes, and in that setup, the routers do not sleep, and we really need to have all nodes with the capability to sleep to lower the power consumption. And so on this module itself, it also has 6 different 10-bit analog and digital registers. Our inputs will be analog, but they can actually do A to D conversion. And then the input can be up to 3.3 volts, which is very, very helpful because some modules only have an input of about 1.2 volts, and the sensor we are using is actually goes up to 3 volts. And then this particular model has a 90-meter range outside. Some of them have 30 meters, some of them have a much longer one, but it really depends on the firmware that is loaded on it. All right, so this is the pinout for the particular model. And the only ones that we're going to be using in our example are the VCC, which is the power supply, your ground, your reference, and a single analog input. Now, if you're doing another project, or if you wanted other things to, bells and whistles to add to this, you could add an indicator LED to the on output. You could also add an indicator LED to the network, saying that it's connected to a network or it's not connected to a network. But because this is just a pretty simple example, we're not going to run through that. So this module itself needs to have voltage supply between 2.8 and 3.4 volts. And trust me, you really want to be in between there because it'll burn up really quickly. The current it needs is 50 milliamps in the idle, 45 when it's transmitting, and in sleep mode or powered down mode, it needs 50 microamps. So for the hardware prototype, we're using a 3.3 regulator, a typical 9-volt battery, the XB module like we were talking about, the proto board and adapter, a switch, and then a sensor. This is the schematic for it. Your 9-volt, your switch, your regulator, the potentiometer or sensor. They're pretty much modeled the same way with this particular sensor, and then the breakout board. So here's the actual makeup. Your Zigbee or XB, your switch, your battery, and a nice red covering. 3.3 regulator and then a potentiometer, just because the sensor was too big and made it look funny, honestly. So this is going to be transmitting to the computer, and you can see the coordinator node right here hooked up to your USB and just going into your computer. And so Paul will be talking about the interfacing between that hardware and the software.
All right, so once you plug your XB into your computer, you want to change lots of different settings. And the way to do that is to use the software that XB provides. It's called XCTU. It's a free software, and it's a really good tool. It's got a nice GUI interface. It also has a terminal interface to be able to set their different settings per individual module. All right, so this is a basic look of what the GUI looks like when you plug it in here. Lots of different settings you can change just from right here. A real important button function here is the test button. And you click that, and it'll show the serial ID for that individual module. Each module has a unique ID, and it's important to know what that ID is so you can use it for later in the projects. So like for here, the button was pressed, and you see the long serial number there. So once you have that, the easiest way to do it is to go to the terminal mode. This is where you can type in individual commands and set the data how you would like. So just as a simple example here of changing a simple setting, the first thing you'll do is you'll type in 3 pluses and you'll press enter. And when you type in a command into this terminal and it's successful, it'll return OK. So once you get that OK, you know that your function worked. So for this one here, we wanted to set what's called a pan ID. It'll be explained later what exactly that is, but if you wanted to change this value to something else, you'll type in AT ID and then the number 8. And you press that, and then it'll return value OK. So then you want to make sure that it worked, so you type in ATID, and it'll return the number 8, saying it was successfully made the ID the number 8. And then you want to write this value to non-volatile memory, and you'll type in that command there. It's ATWR, and again it returns OK, meaning it was successful. If it's not successful, it'll return an error, and you can try to figure out what went wrong. And then at the very end, you'll type in ATCN, which exits the command mode, and then the XB is done looking for commands there. So again, this is all used for when you initially configure these. All units will need things such as a pan ID, which again will be explained later, a channel, and the different sleep mode type functions. You also eventually need to let all these nodes interact with what's called a coordinator. And so you'll need to program this setting in to know which node is the coordinator. It was also shown that these also have A to D converters on them. And again, that's a setting that's by default turned off, so you need to turn them on so to let that port function as an A to D converter. And lastly, the coordinator needs to be set in a mode called API mode, and this lets it see data and lets you do more things, which will be explained on the next slide by Jen.
So Zigbees have two main modes it can operate in. The out-of-box mode they operate in is called transparent mode, which would be if you were using these just purely for their networking capabilities, nothing to do with using their A to D converters. These are commonly used in projects with Arduinos, so this would be a mode where just any input, any like data it's getting in, it'll just kind of blindly send out. It doesn't do anything to it, it doesn't collect any data. It's just used purely for being the network interface to send and receive data from other places. This API mode is for use when you are actually using the ZigBee itself for some of that sample collecting. So just the key part highlighted in red is that only an API will show indication of any I/O samples and also any node identification that it would send along the serial number of where the information it is sending did come from. So for sleep mode, there's three different options. An option where it never sleeps, one where it sleeps cyclically, and one where it does not sleep, but it'll send sleep synchronization packets. Andrew mentioned earlier that these things have sleep synchronization. If they all have this same PAN ID and same channel, they'll see each other as a network and try to self-sleep synchronize. So what they do is they go through a nomination process to figure out who is most fit to synchronize their sleep, and that person who ends up being the sleep coordinator sends out packets during every wake cycle to make sure everyone falls asleep and wakes up at the same time. And so they need to be in these sort of compatible sleep mode to also identify each other as being part of the same network. And as mentioned earlier, every XBee has a unique 64-bit serial number. It's something the user cannot change. It's just pre-configured about them. You can see it when you do the test query, when you're interacting within a software way, or it is printed on the back if you don't feel like plugging it into a computer. The way the DigiMesh firmware works on these, everyone who's not a coordinator needs to have a destination address. So if you put it as the coordinator, then it doesn't matter how many, if it doesn't see the coordinator in its network, or if it does, it'll only send data to that address. So at least in our specific example of just sending some analog data across the room, this is the way you would configure them, the coordinator being on the left and the end device here on the right, to set the things that we talked about. And also for setting sampling, you can set a sampling rate here, which it does in milliseconds.
Okay, so once you've configured the whole network and everything's set up, you eventually get the data that you need to use in whatever application you have. It just naturally returns it in hex, which isn't very useful for us. So what they usually suggest when it comes with it is a XBee Python library that you can use to parse through this data and get what you want. And so here's an example script of actually just importing a packet and grabbing it and printing it out. You can see here we use the import XBee from XBee, which is the XBee Python library, import serials. We can actually read from the right port to get the right data. And we open that port, we read the packet, and we print it out. So you can print this up to a file and configure it any way you want. This is what you get from it. And some of the information isn't really relevant, so you probably want to further parse it down. And what we're really interested in here is what node it came from, what the actual value was. They're stored here in the dictionary key value pairs of basically that would be the corresponding voltage. And we use that then, again, we can store this to a file and keep going from there. And that's exactly what we did here. So we open up the file, we store it, we configure the actual 163 that you saw in the previous page into its actual corresponding voltage value by doing just a little small calculation there. We record the timestamp that we're doing that in so we can look at that for later use. And we can take as many samples, obviously, as you want, dictated by the sample rate. And this is very convenient. You can configure it any way you want, and you can display it any way you want. You can store it in, we're probably going to use a JSON format and go put it on a website and do whatever you want with it. So to summarize, basically the whole thing is how to set up an XBee network. First, you need to pick your XBee device, and there's a like we were shown earlier, a big table of different devices based on your power requirements. based on your data transfer rate, based on how much you want to configure it. You need to determine what the power requirements are for that specific device. Be pretty careful with that. And then finally, configure it based on your needs. Some actual XP devices are a lot harder to configure. Ours is pretty easy using the XCTU tool, and that makes it very convenient. Then you have to decide, once you get all your network nodes set up, which one is going to be coordinating all of them, and which ones are just simply going to be transferring data to the coordinator, and what the sleep cycle is and things like that. And then finally, once you've set all that up, you can use a Python script, which they help you with that library, parse through the data, and get what you want from the actual application. So,
Thank you. Is there a quick question? I have a quick one. What gave you the most problem?
that's a good question.
The Python script, the library, was built for a different model than we were using. So, normally you could, to do something like parsing, you could just use the unit.analog sample, just grab the data, but I kind of manually went through the packet like it's a Python dictionary, like a list within a dictionary, and had to do it in a more manual way.